Welcome to Lecture 11, Section 3.4 Uniform Continuity. We are using the text Advanced Calculus by Patrick M. Fitzpatrick, and this is Dr. Gilbert Eyabi. Chapter 3, Section 3.4 Uniform Continuity. For a function f from a domain D to the set of real numbers R, and if x0 is a point in the domain D, we did say that the function f is continuous at the point x0, provided that whenever the sequence xn that is in D converges to the point x0, then the image sequence f of xn converges to f of x0. We did call that the sequential definition of continuity at the point x0. We went further to say that f from D to R is said to be continuous on its domain D if it is continuous at every point in D. Now, there is a concept known as uniform continuity, which requires more than continuity at a point in the domain. We should also mention that uniform continuity plays an important role in the development of the integral, and we will see that later in this course. Subsection 3.4.1 Definition. A function f from a domain D to the set of real numbers R is said to be uniformly continuous, provided that whenever there are two sequences un and vn in D such that the limit as n approaches infinity of un minus vn equals 0, then we would have that the limit as n approaches infinity of f of un minus f of vn equals 0, i.e., to show that the function f from D to R is uniformly continuous, we would suppose that the limit as n approaches infinity of un minus vn equals 0, and then go ahead to prove that the limit as n approaches infinity of the difference of their images would be 0. Limit as n approaches infinity of f of un minus f of vn equals 0. Or further still, we will suppose that the sequence un minus vn converges to 0, and then show that the sequence f of un minus f of vn converges. Let's go ahead and start with a remark which actually could be categorized as a proposition or a small theorem. If f is a function from the domain D to the set of real numbers, and if f is uniformly continuous, then we claim that f is continuous. The reverse is not true, and we will see a couple of examples to demonstrate that. So, suppose f is uniformly continuous on the domain D. Let us prove that f is continuous. So, let's pick a point x0 in D. Suppose there is a sequence xn in D such that the sequence converges to x0. We have to show that the sequence f of xn converges to f of x0, i.e., suppose the limit as n approaches infinity of xn minus x0 equals 0. Call that equation 1. We have to show that the limit as n approaches infinity of f of xn minus f of x0 equals 0. Very easy and very straightforward. So all I need are two sequences such that the limit of their difference equals 0. Let un equals xn and let vn equals x0 for every index n. Then un and vn are sequences in D. The limit as n approaches infinity of un minus vn would simply be the limit as n approaches infinity of xn, because un equals xn, minus the limit as n approaches infinity of x0, because vn equals x0. Observe here that vn is going to be a constant sequence. As n goes to infinity, all the vn's would equal x0 for every n in n. So v1 is x0, v2 is x0, v3 is x0, and so on and so forth. So we have limit as n approaches infinity of un minus vn equals limit as n approaches infinity of xn minus x0 But we know that xn converges to x0. That is the assumption we have here. So the limit as n approaches infinity of xn minus x0 by the sum limit theorem equals 0 right here from equation 1. Recall that our target is to prove that the limit as n approaches infinity of f of xn minus f of x0 equals 0. In other words, the sequence f of xn converges to f of x0. We do know that f is uniformly continuous. So the limit as n approaches infinity of un minus vn equals 0. Therefore, by the uniform continuity of f on the domain D, the limit as n approaches infinity of f of xn minus f of x0 equals the limit as n approaches infinity of f of un minus f of vn. But because we have this statement here, by the uniform continuity of f, this equals 0. So what have we done? We have actually shown that the limit as n approaches infinity of f of xn minus f of x0 equals 0, and that means the sequence f of xn converges to f of x0, and that implies f is continuous at x0. So whenever a function f is uniformly continuous on a domain D, then it is continuous. But we do claim that if it is continuous, it may not necessarily be uniformly continuous. Is there something we can do to a continuous function to make it uniformly continuous? That is the question we would answer before the end of this lecture. But right now, I want us to give a few examples to illustrate the fact that f being continuous on a domain does not automatically imply uniform continuity. Example 1. Define f to be a function from the set of real numbers to the set of real numbers by f of x equals x squared. X is in R. Then f is a continuous function as a polynomial function. F is continuous on the entire set of real numbers. So we have a continuous function. Is it uniformly continuous? Claim no. So we need to provide a counterexample. All we need to do is find two sequences un and vn such that the limit as n approaches infinity of un minus vn equals 0, but the limit as n approaches infinity of f of un minus f of vn is not 0. So let's go ahead and do that. Define un to be n and vn to be n plus 1, then un and vn are sequences in R. The limit as n approaches infinity of un minus vn is the limit as n approaches infinity of n minus 1 over n. This equals the limit as n approaches infinity of negative 1 over n, which is 0 by the constant multiple limit theorem. But the limit as n approaches infinity of f of un minus f of vn would be the limit as n approaches infinity of f of n, because un equals n, minus f of n plus 1 over n, because vn equals n plus 1 over n, and using the fact that f of x equals x squared, that gives us n squared minus n plus 1 over n, all of that squared, and simple expansion, we end up with limit as n approaches infinity of n squared minus 2 minus 1 over n squared. The n squares will cancel out. We end up with negative using the constant multiple limit theorem. Limit as n approaches infinity, 2 plus 1 over n squared. The component 1 over n squared as n approaches infinity converges to 0. So all of this converges to negative 2, which is different from 0. Therefore, f is not uniformly continuous. We have found two sequences un and vn in the domain such that the limit of their difference is 0, but the limit of the difference of their images is not 0. So uniform continuity doesn't hold here. F is not uniformly continuous on R. Let's take one more example. Example 2. Define the function f from the open interval 0, 1 to R by f of x equals 1 over x, where x is in the open interval 0, 1. Then f is continuous as a quotient of two continuous functions. The constant function is continuous, X is a polynomial function, is continuous. The denominator does not vanish in the interval 0, 1 since 0 is not included. Therefore, we have the quotient of two continuous functions and it is continuous. So f is a continuous function on the open interval 0, 1. We claim that f is not uniformly continuous on that domain. Again, we would find two sequences un and vn such that the limit of their difference is 0, but the limit of the difference of their images is not 0. Let's go ahead and do that. Let un be the sequence defined by its n term as 1 over n and vn 1 over 2n. Then observe that both un and vn are sequences in 0, 1. The limit as n approaches infinity of un minus vn is the limit as n approaches infinity of 1 over n minus 1 over 2n, which is the limit as n approaches infinity of 1 over 2n, and that equals 0. But the limit as n approaches infinity of f of un minus f of vn would be the limit as n approaches infinity of n minus 2n, which is the limit as n approaches infinity of negative n, and that gives us negative infinity. It diverges to negative infinity, which is different from 0. We have the limit as n approaches infinity of the difference of these two sequences to be 0, but the limit as n approaches infinity of the difference of the images is not 0. Therefore, we conclude that f is not uniformly continuous on the open interval 0, 1. So is it possible at all? Are there any cases where a continuous function could be guaranteed to be uniformly continuous? Yes, and that is the big theorem of this section. Subsection 3.4.3 theorem. A continuous function on a closed bounded interval AB is uniformly continuous. So yes, a continuous function can be guaranteed to be uniformly continuous as long as the domain is a closed bounded interval. Observe that in the first case, the domain was the set of real numbers, which is unbounded. In the second case, the domain was the open interval 0, 1. It is bounded, but it is not closed. In this case, the domain is both closed and bounded, which means it is compact. So if f is continuous on a closed bounded interval, then uniform continuity is guaranteed. And that would be the last theorem we would prove in this section. Proof. Let un and vn be sequences in the closed bounded interval AB such that the limit as n approaches infinity of un minus vn is 0. Required to prove that the limit as n approaches infinity of f of un minus f of vn equals 0. Let's go ahead and start the argument. We would use proof by contradiction. Suppose the sequence f of un minus f of vn does not converge to 0, i.e., suppose the limit as n approaches infinity of f of un minus f of vn is not equal to 0, but at the same time, the limit as n approaches infinity of un minus vn is 0, and f is continuous on a closed bounded interval. Let's see how we would come up with a contradiction following this assumption. Now, if the sequence f of un minus f of vn does not converge to 0, then by the epsilon n definition of convergence, what we are saying is there exists some epsilon greater than 0 such that the absolute value of f of un minus f of vn is greater than or equal to epsilon for every natural number n. Call that inequality star. We now use the assumption that the domain of f is a closed bounded interval. So by the sequential compactness theorem, there is a subsequence unk of our sequence un and a point x0 in the closed bounded interval AB such that the limit as k approaches infinity of unk equals 0. You can go back and check the statement of the sequential compactness theorem. Now, we do know that f is continuous on the closed bounded interval AB, which means f is continuous at the point x0, since x0 is from the closed bounded interval AB. So, however, f is continuous at the point x0, and that means the limit as k approaches infinity of f of un k equals f of x0. And similarly, the limit as k approaches infinity of f of vnk equals f of x0. Therefore, the limit as k approaches infinity of f of unk minus f of vnk equals 0, because each of these would equal f of x0. That is by the sum limit theorem. But wait a minute. By the inequality star, the absolute value of f of unk minus f of vnk is greater than or equal to epsilon for every k in n, which is a contradiction. Now, this contradiction arises from the assumption that the sequence f of un minus f of vn does not converge to 0. So from this contradiction, we conclude that f is uniformly continuous on a closed bounded interval, and we would have arrived at the end of the proof using the method of contradiction. So whenever f is continuous on a closed bounded interval, we can always conclude that f is also uniformly continuous on that closed bounded interval. And that brings us to the end of section 3.4. I look forward to seeing you in section 3.5, where we will start looking at the epsilon delta definition of continuity and the epsilon delta definition of uniform continuity. Thank you, and God bless you.